So today let's discuss questions related to paraboloid. So the question 1 says that find the coordinates of vertex, focus and length of latest rectum of the principal section of this paraboloid given by this equation. So if you see that this question is not actually related to paraboloid specifically, but it is basically a 2D question. But since the question mentions the word paraboloid, so we are discussing it here. So the question says that we're supposed to find vertex, parabola, vertex, focus and length of latest rectum of the principal sections of this paraboloid. So the given equation of paraboloid is x square by a square plus y square by b square is equals to 2z by c. And my principal sections will be basically when x equals to 0 and when my y equals to 0. So there will be two cases. First will be when I'll assume my principal section to be x equals to 0, and then we'll find vertex, focus and latest rectum length. Likewise we'll do it for another case when I'm taking y equals to 0. So let us solve it. So case 1, when principal section is x equals to 0. So if I put x equals to 0 in given equation of paraboloid, I'll get basically y square by b square is equals to 2z by c. So from here I got y square is equals to 2b square by c into z. So if you see that this is basically equation of a parabola in yz plane. So you can observe that its vertex is basically 0, 0 in yz plane. Vertex is basically 0, 0, and for parabola of form y square is equals to 4az. So my focus is basically 0, a. So I'll basically compare these two parabolas and will find focus. So my focus is 0, if I compare 2b square by c is equals to 4a. So from here I got my a as, let's write it some p, because we have already a in equation of paraboloid. So basically my p is b square by 2c. So my focus in yz plane is b square by 2c, and length of latest rectum is 4b if this is my parabola. So here my length of latest rectum is basically 2b square by 2b square by c. So but we are supposed to find all these for this principal section when x equals to 0. So in x, y, z plane, so vertex will be basically my 0, 0, 0. Focus is 0, 0, b square by 2c, and latest rectum I am representing by LR. Length of latest rectum is basically 2b square by c. Likewise for case 2, when principal section is my y equals to 0. So when y equals to 0, if I substitute it in the given equation of paraboloid, I'll get x square by a square is equals to 2z by c. So from here I got x square is equals to 2a square by cz. So this is basically my equation of parabola in xz plane. And like we did for part 1, so we can find out that vertex will be basically 0, 0, 0. Focus will be 0, 0, a square by 2c, and LR, that is basically length of lattice rectum, will be 2a square by c. So we are supposed to do this in this question. Let's move on to next question. So the next question says that prove that in general 3 normals can be drawn from a given point to this paraboloid. So if they have given us a general equation of paraboloid, that is basically x square plus y square is equals to 2az, and they have asked us to show that this paraboloid have basically from a given point 3 normals can be drawn to this paraboloid. So that's what we are supposed to prove in first part. And further it says that if the point lies on the surface of the paraboloid, then 2 of the 3 normals coincide. That is basically there are only two distinct normals, as 2 coincide when the point lies on surface. So let us do that. So this is equation of parabola. Let us name it as 1. So equation of normal to paraboloid 1 at any arbitrary point, let's say x1 y1 comma z1 be x minus x1 upon x1 is equals to y minus y1 upon y1 equals to z minus z1 upon minus a. This will be basically my equation of normal at this point to the given paraboloid. So since it is given that, let us assume that let this equation of normal passes via any point, let's say alpha comma beta comma gamma. So if this passes via alpha comma beta comma gamma, then this alpha beta gamma must satisfy the equation of normal. So using that, I'll get alpha minus x1 by x1 equals to beta minus y1 by y1 equals to gamma minus z1 by minus a. Let us say that it is equals to lambda. So if I equate it with lambda, I'll get basically alpha as x1 into 1 plus lambda, y1 as beta as y1 into 1 plus lambda, and gamma as z1 minus a lambda. So from here I can find out my arbitrary point x1 y1 z1 via which the normal passes. So my x1 point will be alpha upon 1 plus lambda, y1 will be basically beta upon 1 plus lambda, and z1 is gamma plus a lambda. So if my x1 y1 z1 point is foot of perpendicular, foot of normal, then it must be lying on paraboloid. And if that's the case, then x1, y1 and z1 values must satisfy equation of paraboloid. So we'll just substitute x1, y1 and z1 in equation of paraboloid, and using that I'll get x1 square plus y1 square is equals to 2az. So if I substitute it, then I will get alpha upon 1 plus lambda square plus beta upon 1 plus lambda square is equals to 2a gamma plus a lambda. So if I simplify it, I'll get alpha square plus beta square is equals to 2a gamma plus a lambda into 1 plus lambda square. So if you observe that it's a cubic equation in lambda. So if I solve it, so I'll basically get 3 values of lambda, and for those 3 values of lambda I'll basically get 3 a feet of normal from a given, if my normal is passing via a given point alpha comma beta comma gamma. So using that I can conclude that in general a given paraboloid has basically three normals from a given point alpha comma beta comma gamma. So now we are supposed to show that if the point lies on surface, then two of the three normals coincide. So that we'll basically show that using a calculus thing. So let us consider a function f lambda as 2a into 1 plus lambda square into gamma plus a lambda minus alpha square plus beta square. So what we'll do is we'll just take a derivative of this function f dash lambda. So if we solve it, we'll get basically 4a 1 plus lambda into gamma plus a lambda plus 2a into 1 plus lambda square into a. This will be basically derivative. This is basically derivative of f. So if I equate it with 0, so I'll basically get the critical point. So if I equate it with 0, I'll get 2a 1 plus lambda. I can take out as common, so I'm left with 2 into gamma plus a lambda plus a into 1 plus lambda is equals to 0. So from here I got as lambda is equals to minus 1 or 2 gamma plus 2a lambda plus a lambda is equals to 0. So if I simplify it, I'll get 2 gamma plus a upon 3a minus is equals to lambda. So I got basically two values of lambda. So either my lambda is minus 1 or my lambda is minus 2 gamma plus a upon 3a. So if two of the normals coincide, then one of these roots must be, one of these root values of lambda must be root of this f lambda twice. So if we just substitute value of lambda is equals to minus 1 here, then we'll basically get alpha square plus beta square equals to 0, and from there we'll basically get alpha equals to beta is equals to 0, and that doesn't lead us anywhere. So we'll basically be using this value of lambda, because this is also a root of f lambda. So if I substitute it in the original equation, I'll get 2a into 1 minus 2 gamma plus a upon 3a square into gamma minus a into 2 gamma plus a upon 3a minus alpha square plus beta square, and that must be equals to 0 because I am assuming that it is root of f lambda. So if that is the case, so I can solve it. So I'll get 3a minus 2 gamma minus a upon 3a whole square. This a will balance out the 1 in denominator, so I am left with 3 gamma minus 2 gamma minus a upon 3 is equals to alpha square plus beta square. So if I simplify it further, I'll get basically 2a into gamma minus a square upon 9a square into gamma minus a upon 3 is equals to alpha square plus beta square. So if I simplify it, I'll get gamma minus a cube. So here I'll get basically minus 2 gamma plus 2a. So I can take 2 common, and square of that will make the coefficient 8 into gamma minus a cube is equals to 27a into alpha square plus beta square. And I guess this is the relation that we are supposed to prove. 27a into plus a minus z cube. Yeah, so if I take minus common from this term, I'll get 8 into a minus gamma cube is equals to 27a alpha square plus beta square. So from here I will get 27a into alpha square plus beta square plus 8a minus gamma cube is equals to 0. So this is the relation if two of the normals coincide. So the locus of any arbitrary point lying on the surface will be basically 27a into x square plus y square plus 8a minus z cube is equals to 0. So this is the condition when two of the normals coincide if the point lies on the surface of paraboloid. So let us move on to next question. So the next question says that find the equation of tangent plane at point this to the given conicoid. So we know that equation of tangent plane to 3x square minus y square is equals to 2z at any point x1 comma y1 comma z1 is basically 3x x1 minus y y1 is equals to z plus z1. So but I am supposed to find the tangent plane at 1 comma 1 comma 1. So I can take my x1 y1 z1 as 1 1 1. So I'll get 3x minus y minus z is equals to 1 as tangent plane to the given equation of conicoid. So let's move on to next question. So the next question says that two perpendicular tangent planes to this paraboloid intersect in a straight line x equals to 0. So given equation of paraboloid is x square plus y square is equals to 2z1, and further says that this equation of paraboloid has two tangent and these are basically perpendicular to each other, and the intersecting line of these two plane is basically intersection line of two tangent plane is x equals to 0. So I can assume that let my plus nz is equals to some lambda be and x equals to 0 be these two, let these two be my tangent planes. And if you observe that using the direction ratio multiplication thing, you'll observe that these two tangents are basically perpendicular to each other. So the question says that these two tangent plane has x equals to 0 as intersection line. So its intersection line will be basically my plus nz minus lambda plus k into x is equals to 0. So if I simplify it, I'll get kx plus my plus nz minus lambda is equals to 0. So the question says that we're supposed to find the curve to which this straight line touches. So this equation of plane that we got basically by intersection of the given tangent planes must also be touching the given equation of paraboloid, and using the tangency condition of a plane to the given paraboloid, we'll basically get k square by 1 plus m square by 1 plus 2 n into p, that is lambda, by 1 is equals to 0. So this we got using tangency condition, that is basically k square plus m square plus 2n lambda is equals to 0. So if you observe that this is a quadratic equation in K. So if k1 comma k2 are its roots, then k1 into k2 will get basically m square plus 2n lambda upon 1, that is coefficient of k. So these, if k1 k2 are roots of this quadratic equation in K, then product of these roots will be this. So from here we got basically direction cosines of two tangent planes whose line of intersection is this, that we assume. So basically our two tangent planes are k1 comma m comma n and k2 comma m comma n, and since these two are basically perpendicular to each other, so from here we'll get k1 into k2 plus m square plus n square is equals to 0. So if we substitute value of k1 into k2 here, we'll get m square plus 2n lambda plus m square plus n is equals to 0. So if we simplify it, we'll get 2m square plus 2n lambda plus n is equals to 0 plus n square, it is n square. So we can divide the whole equation by n square to convert it into a quadratic equation in m by n. So we'll basically get plus 2n into, and my lambda is my plus nz is equals to 0. I have basically substituted value of lambda from here, that I assume as my plus nz. So if I simplify it, I will get 2m by n square plus 1 plus 2 by n into my plus nz is equals to 0. That is basically 2m by n square plus 2m by n y plus 2z plus 1 is equals to 0. So this is basically a quadratic relation in m by n. And if this is basically a tangent plane to the given paraboloid, then we must be having only one root of this equation in m by n. So the discriminant must be is equal to 0. So if we calculate discriminant from here, we'll get basically 2y square minus 4 into a, that is 2, into 2z plus 1 is equals to 0. So if we simplify it, we'll get 4y square minus 8 into 2z plus 1 equals to 0, which is basically y square minus 4z minus 2 equals to 0. So and x is also equals to 0. So this is basically the required curve when the straight line that we got by an intersection of these two tangent planes is touching the given paraboloid. So let's move on to next question. So the next question says that show that the locus of a point from which three mutually perpendicular tangent lines can be drawn to this paraboloid is this. So we have an arbitrary point, let x1, y1, z1 be point from which three mutually perpendicular tangent lines can be drawn to this paraboloid. from which three mutually perpendicular tangent lines are drawn to paraboloid, that is x square plus y square plus 2z is equals to 0. So if you observe that from this point, if three mutually perpendicular tangent lines are drawn to paraboloid, that will basically act as enveloping cone. So we'll basically find the equation of enveloping cone, and this x1, y1, z1 be basically act as a vertex of the cone, because this is the intersection point of these three mutually perpendicular tangent lines with vertex as x1, y1, z1. So equation of enveloping cone will be basically x square plus y square plus 2z into x1 square plus y1 square plus 2z1 is equals to x1 plus y1 plus z plus z1 square. So this is basically the equation of enveloping cone, and since there are three mutually perpendicular tangent lines, so condition for that is basically coefficient of x square plus coefficient of y square plus coefficient of z square their sum must be is equals to 0. So from here, if I see what is coefficient of x square, so that is basically x1 square plus y1 square plus 2z1 minus x1 square. This x1 square, if I'll take it on the left hand side, then that will give me minus x1 square. Likewise, coefficient of y square will be x1 square plus y1 square plus 2z1 minus y1 square plus coefficient of z square is on left hand side, there is no term with variable z square, and on left hand side it will be 1, so that will give me minus 1 is equals to 0. So if I simplify it, I'll get x1 square plus y1 square plus 4z1 minus 1 is equals to 0. So locus of any point via which three mutually perpendicular tangent lines, locus of point P via which three mutually perpendicular tangent lines are drawn to the paraboloid is basically x square plus y square plus 4z is equals to 1, and this is what we are supposed to prove in this question. So let us move on to next question. The next question says that tangent planes at 2 point P and Q of a paraboloid meets in line RS. So let us assume any arbitrary equation of paraboloid. So let ax square plus by square is equals to 2cz be paraboloid. And since there is no information given about point P and Q, so let us assume that point P is x1, y1, z1, and point Q be x2, y2, z2. So the question says that tangent at point P and Q to the paraboloid meet in line RS. So tangent at P will be basically ax x1 plus by y1 is equals to cz plus z1. Likewise, tangent at Q will be ax x2 plus by y2 is equals to cz plus z2. Also, the question says that these 2 points lie on the paraboloid. So if these 2 points lies on paraboloid, so they must be satisfying the equation of paraboloid. Using that, we'll get ax1 square plus by1 square is equals to 2cz1 and ax2 square plus by2 square is equals to 2cz2. So let us name it as 2. So the question says that these two tangent via P and Q meets in a line RS. So equation of line of intersection of 1 will be basically axx1 plus byy1 minus cz plus z1 plus lambda into axx2 plus byy2 minus cz plus z2 is equals to 0. So this is basically the equation of line RS. So the question further says that show that the plane through RS and the middle point of PQ is parallel to the axis of paraboloid. Okay, so we are supposed to show that the plane passing via line RS and middle point of PQ. So middle point of PQ will be, so that will be basically x1 plus x2 by 2 comma y1 plus y2 by 2 comma z1 plus z2 by 2. So our plane via line RS and this middle point of PQ will basically help us find the value of lambda. So my lambda will be basically minus ax1 into x1 plus x2 by 2 plus by1 into y1 plus y2 by 2 minus c z1 plus z2 by 2 divided by ax2 into x1 plus x2 by 2 plus by2 into y1 plus y2 by 2 minus c z2 plus z1 plus z2 by 2. So if I simplify it, I'll get lambda as minus ax1 square plus ax1 x2 plus by1 square plus by1 y2 minus 2cz1 minus cz1 minus cz2 divided by ax2 x1 plus ax2 square plus by2 y1 plus by2 square minus cz2 minus cz1. Here there will be 2 because I will be taking LCM here, and minus cz2. So if I simplify it, lambda will be basically minus of, I can club in these three terms. So I'll get ax1 square plus by1 square minus 2cz1 plus ax1 x2 plus by1 y2 minus cz1 minus cz2 divided by ax2 square plus by2 square minus 2cz2 plus ax2 x1 plus by2 y1 minus cz1 minus cz2. So since we know that x1 y1 z1 and x2 y2 z2 are passing via paraboloid, so from the equation 2 I'll get this term as 0 and this term as 0. So my lambda is basically minus of ax1 x2. If you observe that this term, leftover term on numerator and leftover term in denominator are same, so I'll get my lambda as minus 1. So equation of plane passing via line RS and the middle point will be basically axx1 plus byy1 minus cz minus cz1 plus lambda into axx2 plus by2 minus cz minus cz2 is equals to 0. So this is basically the equation of the plane. So direction cosines of plane via RS and middle point of PQ, let's name it as P dash, will be basically ax1 minus lambda is minus 1 minus x2 comma b y1 minus y2 comma 0. So this is basically equation of direction cosine of normal to this plane, So we are supposed to prove that this plane is basically parallel to x-axis, parallel to axis of paraboloid. So the paraboloid we have assumed has axis as z-axis. So direction cosines of axis of paraboloid are basically 0, 0, 1. So if my this plane passing via line RS and middle point of PQ is parallel to the axis of paraboloid, then the normal to this plane must be perpendicular to axis of paraboloid. So we'll try to verify that. If that's the case, then my plane will be basically parallel to the axis of paraboloid. So if I take product of these two and use the perpendicularity condition here, so I'll get a into x1 minus x2 into 0 plus b y1 minus y2 into 0 plus 0 into 1, that is 0. So my plane is parallel to axis of paraboloid. So that's what we are supposed to prove in this question. So the next question says that show that the plane 3x plus 4y plus 7z plus 5 touches this paraboloid and further find the point of contact. So we have a direct tangency condition. So if ax square plus by square is equals to 2cz is paraboloid and lx plus my plus nz is equals to p is tangent to it, then the tangency condition is basically L square by a plus m square by b plus 2np by c is equals to 0. So I can just substitute value of L, M, N and A, B, C here in the equation by comparing these two equations with these two. So if I do so, I'll get my L as 3, so 3 square, by my A as also 3 plus M is 4, so 4 square, and my B is also 4 plus 2 into N is basically 7 and my P is minus 5 by 2 divided by my C is basically 5. So if I simplify, that must be equals to 0. So if I simplify it, I'll get 3 plus 4, this 2 balances this one and this 5 balances this, into minus 7, which is basically equals to 0. So the given plane is, so the plane and conicoid satisfies tangency condition. So the given plane, that is 3x plus 4y plus 7z plus 5 by 2 equals to 0 is tangent to 3x square plus 4y square is equals to 10z. Now we are supposed to find the point of contact of this tangent plane and the conicoid. So let us assume that x1, y1, z1 be point of contact. Then tangent at x1, y1, z1 to this plane will be to this conicoid will be 3x x1 plus 4y y1 is equals to 5z plus 5z1. So my tangent plane will be 3x1x plus 4y1y minus 5z is equals to 5z1. So these two, if this is tangent plane to this conicoid, then this plane, that is the given plane, and the plane which we have assumed at the conicoid point must be the representing the same plane, then their direction cosines of normal must be proportional. So using that result, I'll get 3x1 by 3 is equals to 4y1 by 4 is equals to minus 5 upon 7 is equals to 5z1 upon minus 5 by 2. So if I simplify it from here, I'll get my x1 as minus 5 by 7, y1 as minus 5 by 7, and my z1 as 5 by 14. So basically my point of contact is minus 5 by 7, minus 5 by 7, comma 5 by 14. So let's move on to next question. So the next question says that prove that the normal from this point to this paraboloid lie on this equation of cone. So for that equation of any line via alpha comma beta comma gamma will be basically x minus alpha by L is equals to y minus beta by M is equals to z minus gamma by N, where I have assumed L, M and N to be arbitrary direction cosines of that line. Further, if x1 comma y1 comma z1 is any point on paraboloid, then equation of tangent at this point x1 y1 z1 to paraboloid will be basically x1 by a square plus 5y1 by b square is equals to z plus z1. So direction cosines of normal will be at x1 comma y1 comma z1 will be basically x1 by a square comma y1 by b square comma minus 1. Also we have assumed that this line is normal to the given paraboloid, so the direction ratios must be proportional. So using that we'll get L upon x1 by a square is equals to M upon y1 by b square is equals to n upon minus 1. So if we equate it with k, so we'll basically get values of L, M and N. So that is basically L is k into x1 by a square, M is k into y1 by b square, and N is basically minus k. Also, I am able to equate this direction cosines of a normal and the direction cosines of normal to the tangent at x1 comma y1 comma z1 is because my x1 comma y1 comma z1 point is also passing via a normal. So using that I'll get x1 minus alpha by L is equals to y1 minus beta by M equals to z1 minus gamma by N. Then basically my x1 will be, that will be basically foot of normal, foot of this normal, and that will be basically, I can calculate that using like by equating it with some term lambda, so that I'll get x1 as basically a square alpha upon a square plus lambda, and y1 as b square beta upon b square plus lambda, and z1 as gamma plus lambda. You can use this directly as well for general equation of paraboloid. Also we have calculated it above as well in one of the questions, that this will be foot of perpendicular basically. Let me just show you that. Yeah, here we calculated, and here we have assumed a to be 1 because in this parabola we assumed a to be at 1 and likewise b, so that's why the result varies. So you can calculate the foot of perpendicular like this. So I got this as basically foot of perpendicular of this. So from here I get my L as basically k by a square into x1, that is a square alpha upon a square plus lambda. Likewise my m will be k by b square into b square beta upon b square plus lambda, and my n is basically minus of k. So if I simplify it, I will get L as k alpha upon a square plus lambda, m as k beta upon b square plus lambda, and n as minus k. So from here I can find out a square plus lambda as k alpha upon L, and b square plus lambda as k beta upon m. So if I, and n is basically minus k, if I subtract this from this, I'll get a square minus b square as k alpha upon L minus beta upon m. So that is basically a square minus b square is equals to, and my k from here is minus n into alpha upon L. So from this equation my L will be basically some constant times x minus alpha minus beta upon y minus beta. So if I simplify it, I'll get a square minus b square plus n times alpha upon x minus alpha minus beta upon y minus beta is equals to 0. I guess this is what we're supposed to prove in the question. Alpha minus upon z minus gamma as well. Okay, I can just substitute n with this and take it on the other hand side. So I can replace, using 1 I can replace n by z minus gamma. So that will give me alpha upon x minus alpha minus beta upon y minus beta is equals to 0. So if I divide it by z minus gamma, I will get a square minus b square upon z minus gamma plus alpha upon x minus alpha minus beta upon y minus beta is equals to 0. This is the term that we're supposed to prove, I guess. Alpha upon x minus alpha minus beta upon z minus gamma. Yeah, so this is the relation that we're supposed to prove. So only these many questions are asked related to paraboloid. So thank you for watching.